Greetings, this is Greg. The P-51H was the ultimate P-51 Mustang. This video is a part of my Superprop series. I'm defining Superprop as a piston-powered, ultra-high-performance combat aircraft that did not see combat in World War II. I briefly talked about the P-51H in an earlier episode that focused mainly on the Republic XP-72. At the time I made that episode, I underestimated the interest in what I'm calling superprops and didn't realize this would turn into a series. Now that it has, the P-51H needs its own dedicated episode, so here we are. The other superprops I have covered so far are the Republic XP-72, the Grumman F-8F Bearcat, the Supermarine Seafire 47, and the Hawker Sea Fury. The XP-72 never went into production. Of the other three, I think the Sea Fury is the best one for reasons that are explained in the previous videos in this series. So the Sea Fury is primarily what I'll be using for comparison with the 51H. Of course, the 51H starts with an obvious advantage in that it doesn't have any sacrifices made for aircraft carrier duty, which gives the designers the ability to bias it a bit more for performance. The downside is the superprops, which could be operated from carriers, were much more relevant than those that couldn't, at least in regards to single-engine superprops, which are all we've looked at so far. A land-based single-engine superprop was already totally obsolete, even in 1946, because of the new jet fighters going into production. For example, Republic's F-84 Thunderjet, which first flew in 1946, could far outperform any of the superprops in most aspects. This plane would itself be made obsolete by the new swept-wing jet fighters like the F-84F Thunderstreak. The F-86 Sabre first flew in 1947, and with its jet power and swept wings, it completely closed the door on piston-powered fighters. Well, I shouldn't say completely. There were still a few situations in which piston-powered fighters were still relevant. The new jet fighters had very short range, so it was thought that the piston-powered fighters might still have a place as long-range bomber escorts. Second, some countries just couldn't afford the new jets. They were expensive. However, there were plenty of World War II surplus aircraft on the market, making second-hand P-47s or P-51s look like a pretty good deal. And we did see these planes in service with Taiwan go up against the communist Chinese forces with great success in the early 1950s, something that seems to be getting scrubbed from the internet. Last, naval aviation took some time to adapt jets to carrier duty, and even longer to adapt the higher-performing swept-wing jets. So the piston-powered fighters stayed relevant in naval service a bit longer than they did otherwise. Let's get into the P-51H. I need to make it very clear that while it looks a lot like a P-51D, it was, as is written in the pilot's manual from North American, an entirely new design. The 51H is easily recognized because of its straight leading edge. The earlier production models, have a kink in the wing near the fuselage, like this D model here. These previous P-51s, like the D model, used the NACA 45-100 airfoil. This was a low-drag design and with pretty good characteristics at what were high Mach numbers for the time, generally around 0.8 or 0.8 the speed of sound. The wing is often called, somewhat incorrectly, a laminar flow wing. I have an entire video on that subject here. For now, just know that it was a good wing with low drag and a step forward at the time. The P-51H uses a newer wing design, which was the NACA 66 series. This was a late war airfoil and was an evolutionary step forward from the earlier 45-100. This newer wing design was also used on Bell's P-63 King Cobra and the P-82 Twin Mustang, and it was almost identical to the airfoil design used on the Douglas A-26 Invader and Lockheed's P-80 Shooting Star. This wing, and especially when combined with North American's excellent build quality, again, see this video, gave the plane very low amounts of parasite drag, making the plane quite fast for a given amount of horsepower and/or fuel flow. Speaking of horsepower, there was a big change up front. The P-51 was powered by the Packard Merlin V1650-9. Earlier Merlin-powered variants like the D model typically had a Packard V1650-3 or a -7. The -9 had some big upgrades. First of all, it has water methanol injection. I always found it odd that the British sort of shunned water injection in World War II, especially considering that water injection was invented by the British and advanced by Sir Harry Ricardo, probably the most important figure in aircraft engine development ever, and he was British. Yet in World War II, neither the Rolls-Royce nor the Packard Merlins ran with water injection operationally. Meanwhile, the Daimler-Benz, Junkers, Pratt & Whitney, Nakajima, and others were fully on board the water injection bandwagon. This may have something to do with the fact that the Merlin didn't really need it. With dual-stage supercharging and burning 150 octane fuel, they could run manifold pressure numbers of 75 or even 80 inches of mercury, generally higher than those other engines, even with their water injection. Of course, that has a lot to do with the fact that those other engines were either air-cooled or running on much lower octane fuel, another topic I have an entire video on here, so no point in repeating myself. If this is the type of content you enjoy, please like and subscribe, and you may want to consider joining my Patreon. I have the pilot manuals for most of these planes there, as well as colored PDFs of aviation magazines from the period with relevant articles, and many other source documents and books you might enjoy. Patreon supporters also get to vote in polls to determine the direction of this channel and engage in discussions you won't find elsewhere. Back to the video. The P-51H was set up to run 90 inches of manifold pressure, and the normally quoted horsepower at that setting was 2,220. More importantly is the amount of power it had throughout a wide range of altitudes due to the Merlin's excellent dual-stage supercharger, intercooler, and aftercooler. It had better than 2,200 horsepower from sea level up to 10,000 feet. It's actually as high as 2,270 at some specific points in terms of airspeed and altitude. At 25,000 feet, it can still make 1,700 horsepower. On the official aircraft characteristics chart from the U.S. Air Force, they list the horsepower as 2,220 and the fuel used as 145 octane, although it could run on 130 octane at 80 inches of manifold pressure for a little less power. The other big change to the engine was the addition of the Simmons control unit. This greatly simplified the pilot's operation of the engine by managing the air-fuel ratio, the manifold pressure, and the water injection. Now, the air-fuel ratio is pretty easy to understand. The mixture control now had only two positions: idle cutoff for shutting down the engine and run. When in the run position, the system would meter fuel to give the engine the ideal air-fuel ratio for all conditions. The pilot would move the control to the run position during start and leave it there until shutting down the engine. This mixture control had been improving in U.S. fighters and specifically in the P-51 during the war, but the P-51H had the easiest version yet. Many earlier U.S. fighters, including many but not all the P-51Ds and Ks, required the pilot to switch between auto-rich and auto-lean depending on the power setting, and screwing this up could cause a loss of power, engine damage, or worse. So it was a big thing which could be easily forgotten during combat. Here is a chart for it from the P-51B manual. You don't want to mess this up. However, it's just not a factor in the 51H. The pilot doesn't need to think about it. The H also has automatic manifold pressure control. Let me explain what this means. In many airplanes, when climbing with the throttle set at some value, say 42 inches of manifold pressure at whatever RPM has been selected, the manifold pressure will drop by about 1 inch every 1,000 feet due to the decrease in atmospheric pressure, and the pilot will counter this by moving the throttle lever forward a bit during the climb every minute or so. That means that the pilot would have to take his eyes off the sky and look at the manifold pressure gauge for a brief moment while making the adjustment. And this wasn't really a desirable thing to have to do when you're flying over enemy territory. And when descending, it's much the same. Every 1,000 feet or so, you have to pull it back a little bit. Now, most aircraft, or at least many of them in World War II, required some amount of pilot attention to manage this. Most P-51 Mustangs did not require this, as they had automatic controls to manage it. The pilot sets the mixture, manifold pressure, and RPM, and it tends to stay put while climbing and descending, which was nice. Now, in the P-51H, this was improved, and it worked throughout a greater range. The water injection system in the 51H was user-friendly as well. It had an off-on switch, which was really an off-armed switch. That's a better way to think of it. When the switch was on, the system was effectively armed. Then, with the switch in that position, if the throttle was moved forward past the takeoff stop, the water injection would turn on, and manifold pressure would rise to either 80 or 90 inches, depending on how it was set up. Operationally, this worked very much like Germany's FW-190 Dora 9. It's armed by a switch and then activated or deactivated by throttle movement. I think this was the best way to do it. In the 51H, once the supply of water was used up, which was only 10 gallons, enough for about 7 minutes, the regulator would automatically pull manifold pressure back to 67 inches to prevent damage to the motor. And 7 minutes was the limitation for operating the engine at that power. So the pilot didn't need to monitor this too carefully. He didn't need to worry about blowing the motor by running too much manifold pressure without the water spraying. The cockpit in the 51H was very much like the one in a late model P-51D. It was not the same, but close enough to make it an easy transition from one plane to another. The 51 always had a somewhat user-friendly cockpit. It wasn't quite as good in this regard as Germany's FW-190s, but it was still good by World War II era standards and a bit better than most of the other U.S. fighters at the time. Moving on, I think we all know that during the war, new versions of existing fighters were coming out all the time. The Spitfire Mark IX came out after the Mark V. The 109G followed after the 109F. The bubble-top P-47s followed the Razorbacks, and so on. In all of these cases I just mentioned, the subsequent models were heavier than their predecessors, and that was the norm. But it's not the case with the P-51H. It's about 600 pounds lighter than a D model. In fact, making the plane lighter than the D model was a design goal. The plane started off as a lightweight Mustang project and went through various prototypes like the F and G models before settling on the H model for production. According to various secondary sources, and I think the story is true, Edgar Schmude, the plane's designer, and I hope I'm saying his name close to correctly, it's spelled S-C-H-M-U-E-D. Anyway, the story is, he went to England and talked to people at Supermarine to figure out why the Spitfire was so much lighter than the Mustang. Of course, some of those reasons were obvious. All of the Mustang's fuel tanks were self-sealing and much larger and heavier, as the Mustang had far greater fuel capacity than a Spit 9. But still, that doesn't account for all the difference. It turned out that a lot of the difference was because the Mustang was simply built more heavily in almost every way. For example, the Mustang was built to take much harder landings. Thus, its landing gear was stronger and heavier. The engine mounts on the Mustangs could take larger side loads, probably way beyond what the pilot could induce anyway, because I haven't heard of motor mounts in U.S. World War II fighters cracking or failing because of side loads, but maybe it happened, but if so, it was rare. So a lighter engine mount structure and lighter landing gear helped to save some weight. It also had smaller wheels, and they incorporated disc brakes, which were unusual at the time. The fuselage was slightly more narrow than the previous P-51s and used a newer type of aluminum that was thinner and lighter. These efforts and others ended up making the plane about 600 pounds lighter than a D model, and at a time when the weights of the other fighters were going up. For comparison, the empty weight of a P-51H is listed as 6,551 pounds. That's a late 1940s production model with all the standard equipment bells and whistles aboard. When you compare that to other late war piston engine fighters, and especially to other superprops, it's pretty light. Lighter than a Spitfire Mark 14, lighter than an FW-190 Dora 9 or an FW-190A8. It's also lighter than a Bearcat or a Seafire 47, which are two of the lighter superprops. One of the interesting changes they made to the P-51H was to the oil cooler. Most P-51s cooled the oil via an air-to-oil heat exchanger, basically like a radiator in your car, but for oil. And it was located in the cooling duct before the engine radiator. Now, this worked just fine and was the standard way of cooling the oil in World War II aero engines. But it's also a vulnerable spot. If a plane takes a solid hit to the oil cooler, it's almost always going to lose the engine that's associated with that oil cooler in a short amount of time. They did something different on the 51H, and I think it was a good idea. They located the oil cooler in the engine compartment and cooled it via a coolant-to-oil heat exchanger, not air-to-oil. The coolant-to-oil heat exchanger shared coolant with the aftercooler. One advantage of this is it puts the oil cooler in a much safer location and eliminates a lot of the oil lines. The system is less likely to be taken out by a single bullet. Now, if a bullet hits the heat exchanger for the aftercooler, which is still located in the lower scoop, then the engine loses both aftercooling and oil cooling. But without aftercooling, the engine will have to run at reduced power anyway, so the oil cooler is less important at that point. I suspect the plane could still easily make it home in this situation with reduced power. Liquid-to-oil coolers have become very common in recent times. Most modern turbocharged cars have them, but it's interesting to see that these have been in use since World War II. My Fiat 124 has such a cooler from the factory. So does my Alfa Romeo Giulia 2-liter. And they work very well, even at the significantly elevated power levels I'm running in both of these cars. I do own one American turbocharged car, and from the factory, it has no oil cooler at all, which I find very annoying. I'm testing it at the racetrack in this picture, and I blurred it out because I'm not authorized to talk about the upgrades in development for the car, which are for a particular vendor, which is somewhat secretive. And I don't want to give out any clues. Anyway, the car's manufacturer clearly knew that it should have an oil cooler because they got around this by putting a statement in the owner's manual that before you take the car to the track, you should change the oil to a heavier weight, and then you have to change it back to the regular weight oil after the track event. And it's a pain in the butt to change oil twice for every time I go to the track. I'm doing a lot of testing and development on the car at the moment, and I'll let you guys know more about this project in the future. Back to our airplane. North American found that the earlier Mustangs would suffer noticeable performance losses due to even very minor damage to the wings, small dents, scratches, and such. This type of damage would often happen in normal usage. For example, when the 6 machine guns were being serviced by the armorers, they would often cause this type of minor damage, which in most airplanes wouldn't matter much, but the P-51's wing was super sensitive to little irregularities. To minimize this on the 51H, they made the guns a lot easier for the armorers to service, thus reducing the chance of performance-robbing damage. The fuel system on the 51H was significantly improved versus the earlier models. More correctly, the way the fuel system was installed improved the plane. Let me explain. The Merlin-powered P-51Bs originally had this fuel system with 2 internal fuel tanks located in the wings with about 90 gallons each. This is the fuel system the plane was originally designed with. However, they decided to add fuel capacity by adding an 85-gallon auxiliary fuselage tank behind the cockpit. Most of the older P-51Bs were retrofitted with this in the field, and it became standard for production planes at some point. The downside was that it created a center of gravity problem, which makes sense because the tank itself is heavy, and the fuel in it adds about 6 pounds per gallon, and it's all way back there. This rearward center of gravity made the plane difficult to fly in combat-type maneuvers. I suspect you can read this restriction from the pilot's manual a couple of different ways, but in practice I can tell you that P-51 pilots burned fuel out of the fuselage tank before the drop tanks in order to get the center of gravity far enough forward so that the planes would perform normally in combat. This adversely affects the plane's combat radius because when the enemy is sighted, the pilot drops the external tanks, but then doesn't have full internal fuel because he already burned a lot out of that rear tank. This wasn't really a problem for the 51D in Europe because the plane could fly to Berlin, fight for a short time, and still get back home, even with this drawback. But it's not a desirable situation. So the 51H, being a clean slate design, incorporated a rear fuel tank from the start. There was no center of gravity issue with the 51H fuel system. It's interesting to note that the total fuel capacity in the 51H was actually a bit lower than the 51D. However, when going into combat, when both planes drop their external tanks, internal fuel is probably going to be slightly greater in the H model in most cases, so its combat radius won't suffer as a result of the slightly decreased capacity. In short, while it was a new airplane, the 51H can be thought of as a P-51 Mustang with all the improvements they could throw at it and the lessons learned up to that point. So how does it perform? Well, sadly, there are not a lot of tests of this airplane, which is typical of the superprops. The interest had moved on to jets by this point. That said, we do have some good data for the plane, but with some fairly widely ranging results. And this is partially because some tests were at 90 inches, some at 80 inches. Some of the tests were on very early pre-production examples, which were not truly representative of the production planes that were in service in the late 1940s with functional weapons, normal production tolerances, all the antennas for the extra electronic equipment they were putting, or electrical equipment, I should say, they were putting in place. Plus, the weights for the tests varied, as well as the radiator flap positions used and more. The pilot's manual I have for this airplane is from early 1945 and assumed 80 inches of manifold pressure on 130 octane fuel, probably because at the time it was written, they planned to send those planes to the Pacific, and I don't think they were using the 150 octane fuel out there at the time. However, the chart I have on screen right now is from a 1949 document from the Air Material Command. This is as official as it gets, so these are the numbers I'm going to use. Note they are in knots. I'll convert that to other units for you in a moment. The document specifies the Merlin-9 running 145 octane fuel, making 2,220 horsepower, which clearly says that it's running at 90 inches of manifold pressure. However, that is not specifically mentioned in the document. Let's graph this out in miles per hour and metric so we can compare it to the Sea Fury and the others. The maximum speed of the P-51H, according to the chart I'm using here, is 409 knots, which works out to 471 miles per hour. Now that's smoking fast for a prop-driven fighter, especially considering that I'm using the most conservative results out there for this airplane. But again, I'm also probably using the most realistic results for a production P-51H in service. Now, there are results for this airplane showing a top speed up close to 490 miles per hour, but the vast majority of data for production P-51H models gives a top speed of just over 470. Let's keep in mind that there is some faster data out there for the Sea Fury as well, and I go into detail about that in the Sea Fury video. But for comparisons, I'm going with the most official data I can find that's reflective of a production airplane in service. Enough about that. Comparing climb rates when using that same standard, the P-51H comes out on top here as well. It's just very hard for the naval fighters to win in a straight-up performance comparison. Compared with the Sea Fury, the P-51H is much lighter, has a lower wing loading, a much lower stall speed, and a better power-to-weight ratio. It can outrun, outclimb, and outrange the Sea Fury, and the Mustang, with its lower stall speed, is going to beat it in turn performance and in sustained turn performance, due in part to the Mustang's superior power-to-weight ratio. However, Even with all of that said, I still have to lean slightly towards the Sea Fury here for a few main reasons. First, the Sea Fury has a successful combat record. The P-51H doesn't have a combat record at all. In Korea, the U.S. sent P-51Ds, not H models. That was largely a logistical choice. Not that many H models were built, only about 550 of them, and there were not a lot of spare parts for them. By contrast, there were many D models and tons of spares from the war, so it was just easier to support them in a faraway theater. I have seen comments that the H was thought to be more fragile, which is probably true, but the preponderance of evidence is that the U.S. sent P-51Ds to Korea instead of H's for logistical reasons. Now, had the H served in Korea, it probably would have done well. The issue for me is that the Sea Fury did do well, and I've seen many cases when a plane that looked good on paper and you would think would have done well in combat just didn't do well in actual warfare. We see that all the time with post-war Soviet Union stuff. Their fighters always appear to be about equal to the U.S. fighters. Then when the shooting starts, the U.S. planes normally have a kill ratio of 14-1. 30-1, or even 80-1. Now, there are a lot of reasons for that, and I'm certainly not going to go into those reasons in this video. But the point is that while the P-51H probably would have done well had it gone to war, we can't say for sure, and the Sea Fury actually did do well. The next factor to consider is that the Sea Fury was a naval fighter, and for reasons I talked about earlier in this video, that alone is a big advantage when talking about superprops. The non-naval superprops just didn't matter as much. The last thing to consider is that the Merlin engine in the P-51H was at the end of its development. The Bristol Centaurus in the Sea Fury was near the beginning and had much more room for upgrades and power. In fact, it wasn't long before we saw that engine with 3,000 horsepower, although not in the Sea Fury. But had the superprops stayed around longer, I think the Sea Fury would have got that upgrade. I should also add that the P-51H has 50 caliber M2 machine guns, which were great, but these were the World War II 50 cals, not the much faster firing M3s used in the F-86 Sabre. The M2s were good weapons, especially by World War II standards, but the 20 mils in the Sea Fury were better. In the next video in this Superprop series, I'm going to bring in a naval fighter that I think will match up really well with the mighty Sea Fury. I'm really looking forward to making that video, but I have a few others I need to finish first. Thanks for watching. I want to thank all my subscribers and especially my supporters on Patreon. That's all for now. Have a great day.